All right. In this video, we introduce the notion of sets, and sets are the very foundation of mathematics because every mathematical notion is built on some kind of set. So let's begin. So we define a set very informally. Okay, a set is a collection of distinct objects. Distinct objects. Okay, so this part, distinct, is important. So for example, if we have a collection of some natural numbers, 1, 2, 3. So this is a set consisting of 3 elements, 1, 2, and 3. And 1, 1, 2, this is not a set according to our definition because this one, and this one, they are not distinct. We cannot distinguish these between these two ones. So this cannot be a set. Okay, so this is an important restriction imposed on the definition of a set. And the members of a set is called elements. Okay, and if something belongs to a set, we write like this. So let's say S is a set and A is an element of that set S, then we write A is an element of S like this. So this is a symbol representing the membership of an element. So in this example, let's say we name this set as S. Okay, so S is a set consisting of 3 numbers, 1, 2, and 3. So 1 belongs to this set S. And 2 also belongs to this set S, and 3 belongs to this set S. However, for example, 4 does not belong to set, so this is not true. So in that case, we write like this. Okay. And similarly, -1 does not belong to this set, and so on. And another important convention about sets is that we do not care about the order of elements in the set. Okay, so again, let's consider this set S consisting of 1, 2, and 3. Then the set written as 2, 1, 3 or 3, 2, 1, and so on, they are all represent the same thing. So this is the same set S. Okay, S is this, and S is same as this and this, and you can use any other orders. Okay, unless otherwise stated, the order doesn't matter. Okay, next, one of the quantities that characterizes a set is the number of its elements, okay? So in this case, we have 3 elements. So in that case, we say that the cardinality of the set S is equal to 3, and that is represented by like this symbol. Okay, this is like an absolute value of S. So in this case, if S is this, then the cardinality of S is 3. Okay, so basically it's the number of elements. When the number of elements is not finite, we say that the cardinality is infinite. Okay, so infinite cardinality can happen. For example, the set of all natural numbers, that set has the cardinality of infinity. Right. Okay, next to cardinality, we introduce a way to compare 2 sets. So suppose we have 2 sets, A and B. If the following holds, we say A is a subset of B. That is, X belongs to A implies X belongs to B. Okay, that means every element of A is also an element of B. So if this holds, then we say A is a subset of B. Okay, we write like this. This is the symbol for representing subset relation. Okay, A is a subset of B. So graphically, this can mean like this. This means like this. Let's say B is something like this. It's a set, and A is completely buried within A, in a sense. Okay, so in this case, every element of A is also an element of B. So A is a subset. Okay, however, this also holds. This always holds. A is a subset of A, whatever the set A is. Okay? Because every element of A is, of course, an element of A. So this is trivially true. Okay? So let's see an example. Again, let's consider S, 1, 2, 3. And let's say T is a set consisting of 1 and 2. Then every element of T, 1 and 2, is an element of S, 1, 2 here, right? So this means T is a subset of S. Or we can say S is a superset of T, okay? Vice versa. A is a subset of B, B is a superset of A. Same thing. Now, if there are two sets, this arrow can hold in the opposite direction. Okay, so in that case, if X is an element of A, then X is also an element of B. And if X is an element of B, then X is also an element of A. So that means if this, then this, and vice versa. The converse is also true. In that case, A is a subset of B, and also B is a subset of A. So both holds, right? In this case, we write A and B are equal. They are the same set, basically. Okay, so if we happen to name S as this set as S, 1, 2, 3 as S, and just someone else may have defined T as 1, 2, 3. So in that case, every element of S is an element of T, and every element of T is an element of S. So in that case, S is equal to T. They are equal sets. And if two sets are not equal, but actually one of them is a subset of the other, then we write like this. Let's say A is a subset of B, but A is not equal to B. In that case, we write like this. And in particular, we say A is a proper subset of B. Subset of B. So proper is here. So if we don't say proper subset, but just if we say A is a subset of B, that may imply that A is actually equal to B. But if we want to exclude this possibility, we write like this and we say A is a proper subset of B. Okay? Next, I introduce the one of the most important set of all sets, that is the empty set. So the empty set is a set that contains nothing. Okay, the empty set. And that is something like this. So there's nothing between the curly brackets. And this is usually represented as this, 0 with slash. Okay, so empty set is this. So it contains nothing. And that's it. So there is the empty set is unique because there's nothing. And so it can be a set, the empty set of integers, empty set of real numbers, empty set of elephants. They are all the same empty sets. Okay? When there are finite elements in a set, then that set can be defined by just enumerating all the elements, such as this. As we have been doing, S is equal to 1, 2, 3. Okay. By the way, we usually use curly brackets to write a set like this. Don't use square brackets or round parentheses unless you define them explicitly to mean a set. Okay, because we use these other types of brackets for other purposes. So just to avoid confusion, just stick to curly brackets to define a set. Okay. So when there are only a small number of elements, then it's okay. We can just write all the elements to define a set. But what if there are like hundreds of elements or even infinite number of elements in a set? We cannot write like this. Okay. In that case, if there are some simple rules, then we can write like this. Even natural numbers can be written as 2, 4, 6, 8, and dot, dot, dot. Okay. I hope the rule is clear. It's just even numbers. So we just add 2 to the last number to get the next number. Okay. So this may be obvious, but sometimes the rules may not be obvious. So in that case, we define a set by using a predicate. Okay, for example, something like this. S is a set where X is an element of some other universal set U, such that P of X is true. So P of X is a predicate, as we learned in the formal logic. Predicate. Okay. So in this way, S is defined like this. So first of all, the elements of S must be an element of some other universal bigger set. Okay? But not only that, each element has to satisfy some predicate. So this predicate must be true for each element of S. Okay? For example, instead of defining the set of even natural numbers, we can alternatively write like the same thing as like this. So X is an element of natural number such that there exists some K which is a natural number such that X is equal to 2 times K. Okay, so in this way, we can define the set of even natural numbers, right? Because every X here in this set E can be expressed as the product between 2 and K, where K is some other natural number. Okay, if such a K exists, then X is defined like this. So therefore, this is, of course, an even number. So in this case, this part is the predicate that decides whether X belongs to E or not. So in this way, we can define more and more complicated sets in any arbitrary way we want. Okay, that's all for this video, and see you later.